In this video, we're going to learn the double angle, power reducing, and half angle formulas, and then do a bunch of examples utilizing these formulas. Let's start with the double angle formula. So our double angle formulas, we'll start with the one for sine. Sine of 2 times an angle theta is equal to 2 times sine of theta times cosine of theta. That one's pretty easy to remember, and it comes in handy when you're trying to simplify things. Now, for cosine of 2 theta, there's actually multiple versions of that double angle formula. So I'm going to erase so I have more room to write all of the versions. Cosine of 2 times an angle is equal to cosine squared of the angle minus sine squared of the angle. But another way to write it is 1 minus 2 times sine squared of theta. And a third way to write it is 2 cosine squared theta minus 1. All of those are appropriate to use when you have cosine of 2 theta. Which one you need might depend on the problem. You should choose the one that looks easiest for your particular problem. And then my tangent double angle formula is tangent of 2 theta equals 2 times tangent of theta divided by 1 minus tangent squared of theta. So anytime we have a double angle inside one of our trig functions, sine, cosine, or tangent, we can use one of these formulas to rewrite it a different way. Let's do some examples using these formulas. First example. Given that sine of theta equals 4/5 for theta in quadrant 2, find the exact values for the following problems. We're going to start with sine of 2 theta. Well, first let me go ahead and draw our triangle. We know we probably will need that. Quadrant 2, we're over here somewhere. So here's a triangle. My opposite is 4, my adjacent is 5. If you use the Pythagorean theorem, you get that this other side is 3. And so I know what sine and cosine are. Remember, cosine is negative in the second quadrant, and sine is positive. Now, using my double angle formula, sine of 2 theta is equal to 2 sine of theta times cosine of theta. And I know sine of theta is 4/5. I was given that. Cosine of theta is negative because I'm in the second quadrant, and then it's adjacent over hypotenuse, so 3/5. When I multiply all of this together, I get negative 24 over 25 as the exact value of sine of 2 theta. I'm going to leave that triangle there because we might need it for the others. Part B, let's find cosine of 2 theta. Well, I have a lot of different formulas for the cosine. I'm just going to use the first double angle formula, which is cosine of 2 theta is equal to cosine squared of theta minus sine squared of theta. Now, cosine of theta, we already said, was negative 3/5. So I get negative 3/5 squared minus my sine of theta, which was 4/5 squared. Simplifying this, I get 9 over 25 minus 16 over 25, which is negative 7 over 25. for the fully simplified version of cosine of 2 theta. So we've done sine of 2 theta and cosine of 2 theta. Now let's do tangent. Find tangent of 2 theta. Well, tangent of 2 theta, using my double angle formula, is 2 tangent of theta over 1 minus tangent squared of theta. And then I just have to plug in what tangent of theta is from my triangle. Now, I am in quadrant 2, so I know my sine is positive and my cosine is negative. That means tangent is going to be negative because it's the ratio of sine over cosine. So I know my tangent is negative. Tangent of theta, opposite over adjacent, I get 4/3, but it's negative. So plug in negative 4/3 for all of the tangent of thetas, and then we just have to simplify. 2 times a negative 4/3, well, that is equal to negative 8/3. And in the denominator, I have 1 minus 16/9. So I have negative 8/3 over 1 minus 16/9 is negative 7/9. And then I can just flip and multiply. Negative 8/3 times negative 9/7. And that gives me positive 24/7 for tangent of 2 theta. All right, so those formulas, they're not too terrible. As long as you know the formula, you can figure out what to plug in to simplify things. The problem is memorizing the formulas. I would highly suggest that you memorize these so that you have them ready in your brain anytime they come up. Now we're going to use one of these double angle formulas along with our sum and difference formulas from the last video to prove a different identity. Let's verify that cosine of 3x is equal to 4 times cosine to the third of x minus 3 cosine of x. So I'm going to start with the left-hand side again and just use my various identities that I know in algebra and simplify to see if I can get the right-hand side. Cosine of 3x. Well, I do know that that's equal to cosine of 2x plus x. Now I can use my sum or difference formulas from the last video. Using my sum formula from the last video, this is cosine of 2x times cosine of x minus sine of 2x times sine of x. But now I need to simplify it more using my double angle formulas. Cosine of 2x. Well, there's a lot of different formulas for that, but I'm going to use that first one again. Cosine squared x minus sine squared x. And I still have multiplying by my cosine of x. Sine of 2x is 2 sine of x cosine of x. And I'm still multiplying by this other sine of x. So now let's see where we're at. I'm going to distribute for this first guy and multiply that stuff together for the second guy. So when I distribute, cosine squared times cosine is cosine to the third. And then I have a minus sine squared times cosine. And for this guy, sine times sine is sine squared, so I have a minus 2 sine squared times cosine. All right, well, this is equal to, by combining like terms, cosine to the third minus 3 sine squared times cosine. Now that's not equal to the right-hand side yet, but we're getting close. I have a cosine to the third, which we want, but what we've been trying to show is something that involved only cosines. It didn't have a sine on the right-hand side. So now I'm going to use a Pythagorean identity to change that sine squared into cosines. I have my cosine to the third minus 3 times sine squared is 1 minus cosine squared times cosine. So now if I distribute everything in that second term, I have my cosine to the third, I have minus 3 cosine of x, and plus 3 cosine to the third of x. Combine our like terms to get 4 cosine cubed x minus 3 cosine x, which was the right-hand side of the thing I was trying to show. So this was a pretty involved problem. You needed to know your sum and difference formulas, your double angle formulas, and a Pythagorean identity in order to show this one. But we know all of those things, and as long as you have them memorized, getting from one step to the next is just a matter of applying the different formulas. So that's all about the double angle formulas. What are these power reducing formulas that I mentioned in the title? Power reducing formulas. We have sine squared of theta is equal to 1 minus cosine of 2 theta all over 2. Cosine squared of theta is equal to 1 plus cosine of 2 theta all over 2. And tangent squared of theta is equal to 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. And so we're going to be using these formulas as well in an example. I would also suggest these formulas, especially the first two, you get memorized, because I know for sure those top two formulas show up a lot in calculus. So if you're planning on taking calculus at some point, you might want to know these memorized in your head. An example using power-reducing formulas. Let's write cosine to the 4th power of x just in terms of first powers of cosine. So I want to rewrite cosine to the 4th so that I only have cosines and there's no powers on my cosine. So the first thing I would do is I would rewrite cosine to the 4th as cosine squared squared. Now using my power reducing formula that we just learned, I can replace that cosine squared with an equivalent statement. Cosine squared is equal to 1 plus cosine of 2x over 2, and now I'm still squaring this. So to square this, the denominator squared is 4. The numerator squared I have to distribute. So I'm going to get 1 plus 2 cosine of 2x plus a cosine squared of 2x for my numerator, all over 4. Now, most of this is okay. I have a 1, which is fine. Cosine of 2x, that's a cosine with no power. But that guy still has a power. Let me split this up into 3 fractions. So I have 1/4 plus 2/4, which is 1/2 cosine of 2x. And then I still have 1/4 cosine squared of 2x. And that's the guy I need to take care of. Using my power reducing formula again, I can change that cosine squared of 2x. So I have 1/4 plus 1/2 cosine of 2x plus 1/4 times, it's 1 plus cosine of something all over 2. Now, in the original formula, it says that cosine squared of x is equal to 1 plus cosine of 2x over 2. The important thing is the input of the cosine squared gets multiplied by 2 in the formula. The input in my cosine squared is 2x. When I multiply that by 2, I get an input of 4x using my formula. So then just simplifying, I have 1/4 plus 1/2 cosine of 2x plus 1/8 times 1 plus cosine of 4x, which I can then distribute my 1/8 and combine that 1/8 with this 1/4. So once I distribute and combine like terms, I'm going to have 3/8 plus 1/2 cosine of 2x plus 1/8 cosine of 4x as my final answer. So this is equal to cosine to the 4th power, but now it's written in terms of cosines with no powers at all. So that's what you would use the power reducing formulas for, to rewrite something so that you don't have powers. Now we have to go over our half angle formulas and do a couple of examples using those. Half angle formulas. Sine of alpha over 2 is equal to plus or minus a square root of 1 minus cosine of alpha over 2. Now that plus or minus just depends on which quadrant the angle alpha over 2 falls in. If sine's supposed to be positive in that quadrant, you would use the positive root. If sine's supposed to be negative, you use the negative root. Cosine of alpha over 2 is plus or minus a square root of 1 plus cosine of alpha over 2. And again, the plus or minus is determined by which quadrant the angle alpha over 2 is in. And then the last formula is the most complicated because there's multiple ways to write it. Tangent of alpha over 2 is equal to plus or minus a square root of 1 minus cosine of alpha over 1 plus cosine of alpha. But equivalent ways of writing this are 1 minus cosine of alpha over sine of alpha, or sine of alpha over 1 plus cosine of alpha. Let me write that last version up here at the top. Sine of alpha over 1 plus cosine of alpha. This guy is also equivalent to those half angle formulas for tangent. So let's do an example using one of these formulas. Use a half angle formula to find sine of 165 degrees. Well, we found something like this before using our sum or difference formulas, but this time we're going to use the half angle formulas. So the first thing I would notice is that sine of 165 degrees, that's the same thing as sine of 330 degrees over 2. Why do I care about that? Well, because now it's written over 2, so I can use my half angle formula. And I know that 330 degrees is on my unit circle. So using my formula, this is going to be a square root of a 1 minus a cosine of 330 degrees over 2. Now we just have to determine, is it positive or negative? Well, the root that, or the angle that I care about is 165. 165 is somewhere over here in quadrant 2. My sine is going to be positive in that quadrant, so I need the positive root. Now we just need to simplify using my unit circle. Cosine of 330 degrees is a square root of 3 over 2. So I can then simplify this root. Instead of dividing by 2, I can flip and multiply by 1/2 and get 1 minus the square root of 3 over 4. Sorry, 2 minus the square root of 3 over 4. So that is flipping, multiplying by 1/2, and then getting a common denominator to write it as one fraction in there. I can simplify the square root a little bit. Can't do anything about that square root of 2 minus square root 3, but the square root of 4 in the bottom is 2. So there is my final answer, fully simplified. Let's do one more example where we are going to use all of the half angle formulas. So if sine of alpha is equal to negative 5 over 13 and 3 pi over 2 is less than alpha is less than 2 pi, find the exact value of various things. First one we're going to do is we have sine of alpha over 2. So first, let's figure out where the angle alpha over 2 is, so that we know if I'm going to have positive or negative for this. Well, if I draw a picture, it tells me alpha is between 3 pi over 2 and 2 pi. So alpha is somewhere over in this quadrant. So let me set up my alpha. I know my hypotenuse is 13, opposite is 5. If I did the Pythagorean theorem, I get that that other side is 12. That's where alpha is. But alpha over 2, I would have to divide all of these. So I know that 3 pi over 2 divided by 2 is 3 pi over 4. That's less than alpha over 2, which is less than 2 pi over 2, which is pi. So that tells me that my alpha over 2 is somewhere over in this second quadrant. It's actually in this little corner piece here, but the important thing is it's in quadrant 2 somewhere. Alpha over 2 is in quadrant 2. That means that sine of alpha over 2 is going to be positive. So using my half angle formula, I have a positive square root of 1 minus cosine of alpha over 2. My cosine of alpha using my triangle is my adjacent, which is 12, over the hypotenuse, which is 13, but it's positive in that quadrant. So I have 1 minus positive 12 over 13 over 2. And that simplifies to, this is 1/13 over 2, which is a square root of 1 over 26. And that can be simplified further if we want to rationalize the denominator. So this is equal to the square root of 1, which is 1, over the square root of 26. And if I multiply both the top and the bottom by square root of 26, I get square root of 26 over 26. That is my simplified version for sine of alpha over 2. The next one we're going to do is cosine of alpha over 2. And again, the first thing you want to do is figure out if it's going to be positive or negative. Now remember, alpha over 2 is somewhere in quadrant 2. Quadrant 2 means cosine is negative. So I need the negative version of my half-angle formula. So there's my half-angle formula with the negative result because I'm in quadrant 2. Now, cosine of alpha, I erased my triangle, but we had it just in the last problem. It's 12 over 13. So 1 plus 12 over 13 is equal to 25 over 13. Over 2 makes this 25 over 26. Then I can take the square root of the top to get 5. Square root of the bottom is square root of 26. And again, multiply by square root of 26 over 26 to get negative 5 square root 26 over 26 as the simplified answer. So we've done sine and we've done cosine. Let's do one with the tangent of alpha over 2. So tangent of alpha over 2, I know my answer is going to be negative because in quadrant 2, which is where alpha over 2 was located, my sine is going to be positive and my cosine is negative. So my final answer should be negative for the tangent. Now, there were 3 different formulas for tangent of alpha over 2, and I'm just going to use the one that said sine of alpha over 1 plus cosine of alpha. I would suggest not using the first version of the formula because it's more complicated, but picking one of the other 2 to try to answer the question. Now I can just plug in my information. Sine of alpha we had was negative 5 over 13. Cosine of alpha we got from our triangle. It was positive 12 over 13. So I have negative 5 over 13, and my denominator is 25 over 13. Then I can flip and multiply by the reciprocal and get a simplified answer of negative 1/5. So that's how you use the half-angle identities to simplify different things. If you have any questions, you can drop them below. If you're a current student, you can also ask in office hours, email, or in person. And I'll see you guys next time.